Thank you for coming to tonight's Science Café, hosted by the Weiss School of Natural Sciences in partnership with the Rice Sustainability Institute, Rice's Carbon Hub, as well as the Consulate General of France in Houston and the Consulate General of Italy in Houston. I'm Tom Killian, the Dean of the Weiss School of Natural Sciences. The Science Café series shares the excitement of scientific discovery at Rice with the general public. Scientific discovery inspires curiosity and it lays the foundations for tomorrow's technological revolutions. It teaches us about the world around us, and it helps us appreciate our roles as collective stewards of the beauty and the complexity of our planet. Through the Science Café, we also seek to build stronger connections between Rice's inspiring faculty and students and the broader Houston community, alumni, and friends. So it's really wonderful to host this event in collaboration with these other entities. So it's my pleasure to welcome, first, Alessio Farino, the Attaché for Science and Technology at the Embassy of France here in the USA.
Thank you. I just want to say that I'm very happy to see that there is so many people here tonight. And for a Franco-Italian scientist like me, it's the perfect night. We have French food, Italian food, and good science. And so it's perfect, and I'm happy to share it with you. It has been a pleasure to work on the organization of this event with the Italian Consulate, with Antonella and Maria Chiara, and with Lauren and Tom team to organize it. And I would like to thank also Aeromid and Maison Marc et Domaine, who offered us the French food that you see there. Thanks to our colleague Joël, who I don't know how she did it, but we don't need evidence. And now I leave the floor to another Florentine, the Consul General of Italy, Mauro Lorenzi.
Thank you. Good evening, everybody. My name is Mauro Lorenzini. I'm the Consul General of Italy here in Houston. And I would start with thanking, special thanks to Rice University for hosting these events. I think the collaboration with universities is really crucial for the challenge of climate change. And I would like to think that this event tonight is like witnessing this importance of the scientific research. I would like to thank also the Consul General of France in Houston for the collaboration to organize this event. But I would also like to recognize the presence tonight of the Consul General of Germany here, so you don't see the flag, but they're all European, and you can imagine that there is also a German flag tonight. I would like, first of all, to recognize the importance, really, of scientific research to tackle the energy transition challenge. It's really a global challenge. Every country in the world is facing this challenge. It's urgent, it's important, because we need to reduce our emission of carbon dioxide to control the climate change. And we need to develop new energy sources, clean energy sources. We need to develop new ways to stock energy and to transport energy, for example, hydrogen. And we need to do it fast. We need to do it urgently. Italy is at the forefront of this process. It participates and actually contributes to the most important European and international initiative for the control of climate change. For sure, there is a lot yet to be done. The emission of carbon dioxide are still very high, and Italy, being like a manufacturing country, of course, is emitting a lot of carbon dioxide. But we are also trying to restructure the whole energy system in Italy. Also, following the Russian aggression of Ukraine, that started really a big restructure of the energy production in Italy. So we are developing the green sources, of course, so eolic, solar, and hydro power, but we need more. In order to challenge the climate change, we need more. We need new technologies. We need new clean sources. And to do this, we need scientific research. Scientific research is really at the core of the challenge. So I like to think tonight, you're going to contribute to this challenge. And I'm sure that the presentation of the two academics that we have tonight here is going to be interesting, and it's going to be something that can, let us think that there is a possibility to tackle this challenge together. So thank you for attending. I hope it's going to be an interesting night. It's a night devoted to science. So let's hear our academics. Thank you.
So tonight, we are fortunate to have two wonderful speakers, one French and one Italian, to tell us about the role of carbon materials in the energy transition. The format is that they will make some brief remarks and frame the conversation, and then we'll start a panel discussion over here, and at some point, we'll have some opportunity to ask questions as well. So, we have Marie Contou-Carrere, who was recently named the Executive Director of the new Rice Sustainability Institute, after serving as the research advisor for Energy Partners at Rice for many years. In that role, Marie worked with corporate research and business senior management and developed and implemented strategies to align Rice's research capabilities with company priorities. She holds a chemical engineering degree from the University of Minnesota and an MS from Central Subec. Matteo Pasquali is the A.J. Harstook Professor of Chemical and Biomolecular Engineering and a Professor of Chemistry and of Material Science and Nanoengineering. Matteo also serves as the Director of Rice's Carbon Hub. He's an expert on carbon materials and production and the relationships with energy systems and carbon dioxide emissions. He earned his PhD in Chemical Engineering from the University of Minnesota and an MS in Chemical Engineering from the University of Bologna. Please join me in welcoming Marie and Matteo.
Good evening, everybody. So, yes, my name is Marie Contou-Carrere. I am the Executive Director of the Sustainability Institute and also the founding Executive Director of the Carbon Hub. So, Matteo and I were delighted to be here to talk to you about our vision to actually utilize carbon as a solution for a sustainable future. So the world currently is facing this double energy challenge. How do we get more energy because the demand is increasing, but how do we limit our CO2 emissions? And it's a bit of a whack-a-mole problem. You have a solution, but then you create more problems. So, for instance, hydrogen. Hydrogen is great. It can really transform the global energy ecosystem, but we don't have any direct sources of hydrogen. So there is a palette of colors that tells you how you make your hydrogen. So it can be pink, blue, turquoise, yellow, black. But the problem is that they all have pros and cons. So in some cases you have a waste stream of solid carbon. In other cases you have a waste stream of CO2. In other cases you need to use a lot of energy. And at the same time, the primary CO2 emission emitters are industry and transportation. And they represent 43% and 25% of all emissions. And those are really hard to cut. So the industrial sector is the hardest of all to attain. Why? Because you really need a lot of energy to make some materials like steel and cement. And you also have chemical reactions that will give you CO2 as a byproduct. So when we look at transportation, well, we're going to lightweight or we're going to electrify. So we put the green points somewhere else in the system. If you lightweight your fleet with other materials like carbon fibers, you actually make your CO2 footprint much worse. If you electrify your car, you put more cables and you make it heavier. So we really have a lot of products that are coming together. It's like we have to slay a hive So, what we want to tell you is that we have to take a carbon shot. We have to use solid carbon as material to build a sustainable future. This is what we will tell you today. So, this higher concept is the way we should think about sustainability, because you really need to take a holistic approach. You need to think about all the consequences of what you are going to deploy. So I wanted to highlight the work by our colleagues at the Baker Institute, where in a recent briefing, they highlight how you have to think about sustainability from a systems perspective. Meaning that you have to address 3 different factors: environmental factors, socioeconomic factors, financial and commercial factors. And all of them are supported by fundamental discovery, innovation, market design, and policy. But you have to look at the whole picture, because you may think you have the best solution, and then you didn't look at the unintended consequences somewhere else. So I highly recommend you go to the website of the Baker Institute, pull the paper, really very nicely. I was hoping that Rachel would be here, so I could point. Rachel? Yes? No, she's not here. So, now, what is the magnitude of the problem?
So, as Marie said, could we use carbon as a material? And in reality, we already use carbon as a material here. Where we have a plot that shows how much materials are we using on an annual basis. And it's a logarithmic plot, so every time you go up a level, it's 10 times more. And so what you see over there on the left, top left, it's coal, oil, and gas, which we really don't use as material, we use it forever. And there's almost nothing of that magnitude. There's only concrete, cement, and brick, and steel that unfortunately. There are some carbon materials at the bottom right, there's carbon fibers, there's carbon black, and a little bit higher up, but there's more. Why is it? Well, first of all, what you notice with this is structural integrity is key for widespread use. If you want to use a lot of a material, it has to hold together. It doesn't have the best material ever. In a plastic bottle, it's not the greatest material, but it holds together and does the job. And the other one is it has to be relatively inexpensive. All of the things at the bottom, carbon fibers, you see some of them, precious metals, etc., they're very expensive. Very expensive because of the production processes. And so we need now a form of carbon that can be inexpensive. You have to have structural integrity, and one possibility is to go and try to displace cement, concrete, and other ceramics. Now, those are really hard to displace because they're cheap. That's exactly what they put into concrete dirt. But there's another opportunity here on the left, which is steel, aluminum, copper, the metal alloys. That's a much better opportunity because the materials have higher value. You start at about $1 a kilo or a couple of dollars a pound for steel, and then you go up and up. And also, they're heavy and they're used in transportation systems with cars, ships, planes. And so, if you use something lighter like carbon, that's a big advantage. The other thing is about half of the industrial emissions come from aluminum, copper, steel, and cement. And so the writing carbon could displace emission from industrial materials. As Marie said, that's not the only problem. This is what's happening now because of the pressure of mining on aluminum and copper. That's the bauxite mine. Bauxite is the mineral that you use to make aluminum. And here, there's another picture of deforestation in Brazil, where they basically clear-cutting forests, damming rivers to extract this mineral. So there's a lot of other issues with going after more metals, and that's why in the developed world, we almost shut down mining. We didn't run out of metals, we just didn't want to keep extracting. So carbon is, rice is a special place. Carbon has always been a special element of rice, and rice is a special carbon. It has been because very small in Montcor in the School of Natural Sciences, about 40 years ago, discovered a new form of carbon. This form of carbon that holds together on a large scale, and they won the Nobel Prize in 1996 for this. But also they built a legacy of faculty. There's Jim Tour over here with the National Academy of Engineering we learned really differently on Wednesday. And also an ecosystem of university institutes and centers, as well as startups and connections to industry. It's also our future. This is where a lot of our graduates are going to other universities to be academic leaders. And so these are, to some extent, the best place to do the work that we're doing on campus.
So, as Matteo showed you, we have a huge problem. The amount we're talking about to move the needle is huge. We're talking gigatons. So, what are we going to do? So, what we're saying is, take your hydrocarbons, don't burn them. Split them into hydrogen and solid carbon. So, that's what is called turquoise hydrogen. So, we're saying, let's go beyond turquoise hydrogen and really put the emphasis on doing something very useful with the solid carbon. So, why is it meaningful? Well, first of all, the splitting process doesn't make any CO2. So that's a plus. And then technological developments the last 2 decades have unlocked scalable processes to new forms of solid carbon, such as carbon nanotubes and graphene. And these materials, particularly carbon nanotubes, have properties that overlap with those of metals in terms of strength, thermal conductivity, electrical conductivity. So that means that now we have in front of us these carbon materials that can be used in a wide range of applications. Yes. They can be used in a wide range of applications, from wires and beams and panels for cars and buildings, all the way to solar panels for farming. And all of these markets that we're talking about are huge. So this has the potential to really move the needle. Because now you can harvest at the same time the clean hydrogen and make sustainable carbon materials that have high value use and low environmental footprint. Okay, yeah, that sounds great. It's not to leave it up, right? No. The future is already here. But it's not evenly distributed. So carbon nanotubes are a great blueprint. And some things are already happening here in Texas. I'm highlighting 2 companies, Dexman and Huntsman. So Huntsman is actually building, it's going to put online its reactor in the next couple of months, I think, right, Matteo? So they're going to make these carbon nanotubes. Dexman takes the carbon nanotubes and puts them in the right shapes to be used. So it can be fibers, it can be foams. And so here, we have some of these materials. And I really encourage you to come, touch them, get a feel, try to break them. Or what? You won't be able to. So you're going to see this is just solid carbon. So it's already happening. There is already the production of these materials. So what is very interesting is that this phenomenon, the fact that the production of carbon nanotube increased and the cost went down, happened without any organized effort. So we are not where solar cells were 40 years ago, or solar cells were 15 years ago. This moved faster than what solar cells did, and that effort was organized. So now we're at a time where we really need to think about how do we accelerate this transition. So what do we need to do?
So what we need to do is what was done with solar about 20 years ago. For example, in the 2000s, the US government decided to set up a sunshop initiative where they decided they were going to take the cost of making electricity via solar photovoltaic and levelize it, so make it equal in cost to coal, nuclear, and natural gas. And that worked. And if you look at how much solar cells, how far they gone, is they were introduced back in the 50s to power satellites at a cost of about $400,000 per megawatt hour. And now they are more than $20 per megawatt hour. And then that didn't just happen because the high end was by, but it happened because of organized effort to sustain over a long time. So now we need to do the same thing that we did on carbon here. So the question we're asking is, how do we push the cost, the levelized cost of these materials down so that it will become first compatible with carbon fibers, high-end steels, copper, aluminum, and then even cheap steel like the one we use in Greenland. And there's really 2 things that have to happen. One is capital has been deployed for scale. This stuff doesn't happen just because time goes by. This capital has to come in and finance the construction of larger plants and finance all the commercial activity that go with using material. But also, we should not stop doing academic research, and because even as the deployment goes, any improvement you can do on the research side will benefit your cost structure and lower your environmental impact at scale. So that's what we're doing. Also, how do you organize it?
No, this is your slide.
Well, so it's something like this won't happen fast enough if we just wait for this to happen organically. If you look at organic introduction of materials, it takes 50 to 70 years for really going to scale. If you look at aluminum, plastics, etc. But if you push, you can reduce that to 20 years. So if you look at certain materials like Kevlar, they went from lab to large scale in less than 20 years. So how do we do this in a situation where we're not a company that can just do it inside? And so how do we organize this and accelerate it so that we push the early stages, which are the least expensive stages in a scale-up process, and get the introduction to the over faster?
So it's because we realize that you need to have these cross-sector collaborations to take the cost down, efficiencies up, and establish a supply chain. That Rice University established the Carbon Hub in 2019, an initiative that brings together industry, academia, and federal labs. So the idea is that we're bringing the supply chain, all the players around the supply chain, from the people who have this feedstock of carbon. It can be hydrocarbons, it can come from biomass, it can be recycled materials, to the industry players that actually will take this carbon and make shapes that you can use, to the end users that will have to take these materials and put them in their applications. So when we launched the Carbon Hub, Shell committed $10 million. Aramco came in just later for another $10 million. So we brought people along the supply chain. Some partners like Brisbane are fundamental to what we're doing, because Brisbane is the world leader in cable manufacturing. And so this funding has also been leveraged to attract more additional funding from the federal government and foundations. And we have also established a vibrant research ecosystem with over 100 researchers in 20 different organizations across 7 countries. So you see the little flag, so one of the great collaborators in Italy. Not yet in France, we do talk to people in France, but they haven't yet participated in our proposals. So, what is this future going to look like?
Well, so, mostly so far, we talked about these switching up music.
Yeah, but they're recording.
Mostly we talked about what to do with the carbon. There's other aspects. There's a feedstock aspect. Right now, we could use oil and gas to make these materials. We already know how to locate oil and gas, how to get it out of the ground, clean it up, and get it to the point of use efficiently. We would not have CO2 emissions because the carbon would be in the material. But also, we could start thinking about using waste plastic. Waste plastic is a low carbon, we don't know what to do with it. Waste biomass, a lot of byproducts in agriculture get essentially landfilled or recycled. And if we start using waste biomass, it's essentially blocking carbon that was blocked by photosynthesis from atmospheric CO2. So it starts being a way to take atmospheric CO2 and block it into long-lived raw materials. And so we can actually address the carbon negative shock. Now we make hydrogen. Marie said that all of these materials here on the left have hydrogen, all these feedstocks, but the carbon material does not have any hydrogen. So hydrogen is co-produced. Some of it can be actually used in these cycles to upgrade feedstocks so that they're usable. And some of them can be used as a clean source of energy. We could use it for other purposes. There's carbon also as granular material. If we make it expensive enough, we could use it to amend the soil. Mazialo here is working and looking at how some forms of this carbon could make soil more productive, reduce fertilizer use, increase water retention. We may be able to use it to remediate soils that have been polluted, like the Superfund Fund. site because carbon can absorb a lot of pollutants. We could use it for water purification. We already do it in our house. A lot of filters are used for carbon, for water and carbon. We can do it in the house. It's too expensive to do on a massive scale. But if the material were cheaper, we could do that on a massive scale. And so we would also, in this way, reduce the water use, increase the water, address the water shop. We could use this carbon to electrify our infrastructure because it's a conductive form of carbon. We can also use it to decarbonize industry by using a material that does not cause CO2 emissions, unlike aluminum and steel. And we could use it to build our environment. The material that is better properties and better footprint. There's another thing that we've been seeing is how important it is to control the supply chain of consoles, and something about this recently. And in a situation like this, one could have jobs that supply security within our offices, essentially. One would not need to send these jobs abroad because the sources of carbon, whether they're fossil or biological, are here, for example, in North America, and Europe likewise has plenty of resources. How big is this if it works? Well, this is roughly how much CO2 you could abate if this goes to scale. We're talking about multiple areas where you could reduce CO2 emissions by between half a gigaton and 4 gigatons. The total emissions are only about 37 gigatons. So if you add them together, it's 65 gigatons. So this is something that happen tomorrow, and it's it's a future that we're creating. We cannot guarantee that it's going to be there, but it's something that it really is worth pursuing because if you think about those wheels that Marie showed at the beginning for sustainability, it really is on top of that. It creates jobs, it creates financial wealth, and it protects our ecosystem. Maybe concluding.
Yes, so when we started thinking about this idea of using solid carbon, it was in 2019, and Bill Gates on his blog has just published a piece where he was saying, if anybody comes to you telling you they have a solution to climate change, you need to ask them, it's not going to show up. And so this is what we're saying. You replace steel. You're going to use solid carbon to create a sustainable future. So I want to thank you for your attention. I would be happy to take questions.
Wonderful, thank you. I hope you enjoyed the comments. So, really interested to hear a few follow-up questions on some discussions here, and then we'll open it up. So, Matteo, the theme here really seems to be using carbon as a material. That's good. You mentioned quite a lot of different forms of carbon. There's graphene, there's carbon fibers, carbon nanotubes. Are they all the same? Can you help us understand what's the differences?
Chemically, yes, they're all carbon.
Your microphone.
The difference between this form of carbons is how they go together. Again, we brought the show and tell. So a lot of carbon is granular carbon that looks something like this. You can play with it. And in most cases, you can't really make any solid materials with this. In this case, this carbon is made by enzyme. You can actually turn it into something like this, which is an object that you can use material you can use to build objects. And there's a type of this carbon which is essentially, it's almost like a polymeric form of carbon. It's long molecules of carbon. They look like these that come out of reactors. And these are the ones that can be made into continuous materials. It was to show you fiber, fiber. And so what is different is really how these carbon atoms are attached to each other at the nanoschale. And for an engineer, that's for scientists, maybe, that sometimes I try to be a scientist. And for an engineer, it's that it all together on a large scale, and that's the hypothesis. And some of them do that.
Hey, Marie, help me understand. So companies are already making these. Is the scale capability already there? What has to happen? What's missing?
There are lots of moving pieces. So the materials get differentiated depending on your application. Then the manufacturing depends on the material. Then the product that you put in place depends on the material. But so all these pieces have to move together. So there is pull, there is push and pull. But it's not even enough to have that solution. You also need to think about, is society ready to accept these technologies? Are policies and regulations that are in place to enable this deployment? Do we have standardization already in place? Because when you're thinking about large volumes, you need to go fast, you have to have the right cost. So all these pieces need to be happening at the same time. That's why we think this is a problem that you can only solve when you really bring the corporations, the academics, the federal labs, the community together to really think about how do we go, where do we put our resources. Please come and talk to us about it. We're very excited. Hopefully we're convincing you that this is worth pursuing, but it cannot be done in a silo. So that's what we're trying to do here. Really open the door and get people to come and really work together.
Yeah, to some extent, we even lack a common language. I was asking this question about what's different about this whole catalog, and we haven't developed a lexicon that lets us talk about each one of those differences. And often I get calls from, especially from startups, they say, "Oh, we're breaking up methane into hydrogen and plasma, and we think that plasma is really valuable." And it's every time someone starts from zero, I understand what is it that they need, and whether they need something that could be made into fiber, or perhaps something that we could ask them to look into for soil amendment, or whether it's something that could only have some very niche value as a disposable material that could be incorporated to another material and so on. So there is a problem of standardization of Western technologies like that. The community is aware of this, but hasn't made it.
And how close are we to that vision of actually taking the hydrocarbons as fuel stock and splitting off the hydrogen and carbon, but actually in a way to actually get energy out?
I think we're about $1 billion. I used to
We take
Let's take a collection.
I used to think about this in terms of time. Then I remember John Hutchinson, who had a quote on his emails like, "Nothing happens until somebody gets up and does something." But somebody can only get up and do something if they have resources. And if you look at where the technology is now, in what resources are needed to really show it at scale, it's about $1 billion. It's not $1 billion check one day, right? It's a staged process where you build progressively larger scale deployments, and then you work with customers to start adopting. You start working with regulatory agencies to get regulatory acceptance, etc. And you may be able to compress it a little bit, or it may take a little longer, but if I think that the need is probably in the ballpark of $1 billion, which I used to think it's a lot of money until I looked at what does it cost to build an oil plant, which is about like $10 billion. Right? I mean, or if you think about a large plant to make plastics right now, or to make steel, you're talking about $5 to $10 billion just to make a plant where we know. So $1 billion, it looks like a lot of money. It's a lot of money for the two of us. They don't pay professional human beings that well. But in the big scheme of things, it's something that is not insolvent. I thought it was all $1 billion.
Fellow University of Minnesota grad. Just wanted to say that carbon is not necessarily a three-dimensional solid that's used in the engineering platform. So you're usually talking about it in something. Are you talking about the traditional in epoxies? And if you do, then you have to generate the oil and gas to make the epoxies, which co-generates CO2. So there seems to be sort of a give and take on creating CO2 and creating the epoxies that that surrounds the composite or the carbon.
Yes, so that's a very good point. And so there's one thing that this carbon can do that carbon fiber cannot do is essentially you can make ropes. You can make textiles that again, you have to come and touch it to really see the difference. Textiles that are very different than the weaves that you make with carbon fibers. So there are a number of opportunities to use this material without using process. The other part is that there's efforts right now to make composites with polyolefins, like polyethylene, polycomposite, and instead of using the process. It's not easy, but there is some early success, and we think that because of the way this material processes, these materials, I encourage you to Google this. You can make an acid with materials in different kinds. It's a carbon fiber, you can do a lateral fit through shaft. Because of those properties, those ability, the mechanical properties, it should be possible to process them with thermoplastics. And then if you go thermoplastics, the CO2 footprint and the energy resources needed are much, much lower than the process. So it's not so much that you need oil and gas. I mean, right now, most of our oil voltages are made from fossil natural gas. But there's actually very little CO2 emitted, and especially if you electrify, the crackers, essentially. So there is a way to do composites where you'll be about 70-80% carbon and 20-30% plastic, but do it in a way that has a much lower resource intensity and CO2 footprint than now.
Now being a material scientist, I'm just wondering about the properties of some of these things that you're trying to replace, and properties like aluminum and copper. You've got conductivity, and you've got ductility, and you've got all of these other properties. Have you done kind of a matrix of all of these replacement materials they're trying to replace with the carbon and their respective properties relative to their applications to be able to understand this mix?
Yes, sir, but it gets actually more complicated because eventually, although we use properties to characterize materials, once we make an object, it's always a number of properties together. I mean, for example, if you look at the plastics, you would never think that polyolefins could replace steel or silverware or wood for furniture based on copper. It's not. There's ways to shape a plastic form. There's a different shape than a metal form. And you compensate with a shape for the fact that the plastic is floppy, right? And even plastic bottles have a certain shape because they're pretty floppy, and that shape gives them a little bit more rigidity so we can hold it. And then you have the next thing is manufacturing is also integrated. So, for example, there's an interesting thing at all the copper wires. All the copper wires we use are oversized in terms of diameter for their electrical function. They're too fragile. And so if you make them any thinner, so there are places, for example, where you can get a material that may not be quite as conductive, but is stronger and lighter, and you can introduce it. It is something in some cases we have to redesign. Like, for example, one of the things that really stuck with me is if you look at stone versus steel versus bridges. If you make an arch bridge, steel is a heavier material because it's heavier, and you cannot carry it in shape on the side. Right? So if you're a Roman brick builder and somebody makes steel, you don't know what to do. So you have to redesign the bridge, and once you redesign the bridge, you have to figure out a different way to build the bridge. And then, of course, the steel bridges now, we can go much larger spans and they're lighter and they're cheap, essentially. So the property matrix tests with that. So in essentially what you see is they're in the same property space. If you look at these fibers, they're stronger than steel, copper, and aluminum. Not quite as strong as carbon fibers, but close. If you look at thermal conductivity, they're better than all of them. Not a whole lot better than copper, but a little bit better. If you look at electrical conductivity, copper is about 3 times better, aluminum is about 2.5 times better. But even if you look at copper and aluminum, even though, for example, aluminum is less conductive, we use aluminum for power lines. Because when you have an overhead power line, the weight goes, copper is so heavy and so soft that if we need the overhead power line of copper, we have to have the power phase really close to the power. So it's less complicated, which is good at that, right? It's valuable because it takes a lot of right people to have those ways to get it done. But that's also good because that's actually an opportunity to create a lot of value, a lot of jobs, a lot of economic value. And that's very exciting.
So, given the presentation, we can see that there is a large scale of carbon application. So that means also business development. I am curious to know what about the energy balance related to the carbon production.
Related to the carbon?
The production, the energy balance.
So there's about 6-7 years ago when the community started paying attention to this, there was a lot of emphasis on the process in which to split the hydrogen and the carbon, and on the paving. And we were a little bit contrarian. We said, don't do that. Focus on the carbon. Because the hydrogen is going to be the same anyway, and the process is just a means to an end. And so I think that what we're seeing now is a lot of the efforts that were started are making carbon that they don't know how to use. Right? So there's some efforts that are making carbon that they can displace carbon back, but that has very limited value and limited total market. And there's some of them are making carbon that you're going to start from scratch and say, what is it that you make, and what is it good for, but it cannot hold together on a large scale. And then there's some efforts that largely were pre-existing coming from the nanotechnology wave of the early 2000s, and now are making this material a larger and larger scale. And so the larger scale reactors are now the big materials that can be into fibers, etc., at about 30 to 50 tons a year. Which, is small, but it's halfway there. If you think about a gram to a ton and a ton to a million tons, a ton is halfway, because this is all logarithmic scale. It's not exponential.
Good question over here.
Yeah, so in the early part of the last century, we were having this same conversation about replacing a large quantity of manufactured products with plastic. And we succeeded in doing that, and now we find ourselves trying to figure out what the implications are in our biological systems of having microplastics permeating every cell. I assume we'll be smarter this time, especially since it's Bryce doing it, especially since there have been some in vitro studies suggesting that there is a fair amount of cellular toxicity associated with the nanotubules. So I'm curious if you could comment about how this evolution of this process should incorporate safety considerations for biological systems.
Yeah, so you're actually completely right. Maybe Marie, you want to say something about how we're doing this? Or?
Go ahead.
He
runs the lab. I let him run the lab.
Sure. No, but this is not a lab issue. I mean, this is something that we, as much as possible, we built into how the carbon operates. This is part of what we see is a problem of nomenclature. So Rachel Michael gives a picture of the own in collaboration with researchers from Mount Sinai in New York. Just wrote a paper where they reviewed hundreds and hundreds of articles what I found is literally is one is even things that have the same name can be very differently based on how they were made in that room. And so that's where the nomenclature problem is. The second one is exposure using right? And this is something that we integrate. It's carbon black, it's fluid added for respiratory exposure, but without any tires, you know, and the tires actually get consumed as you drive. And we don't have this big carbon black problem because as the tires are generated, the particles are generated too large, sticky, or to become a respiratory problem, for example. Other thing is quartz. Quartz is the non-active thing, and it's now PFAS.
Well, asbestos too is like one of the examples of things that are
And
pretty safe as
asbestos-
long as they're in big globs.
No, asbestos is very different. Because asbestos is pretty there was no way to do asbestos safe, right? And they knew this back in the 30s, and they kept it on the rock until it blew up in the 70s, right? But there's a lot of other materials that have respiratory toxicity as well. Because eventually asbestos, the only way you can get asbestos to do something for you, you have to keep it as this variable tubular structure. That's when asbestos is a good thermal insulator. And so it's almost like you're forced to keep asbestos in the dangerous morphology for asbestos to do the job. Whereas this carbon black, you know, you put it into rubber and you make this mixture, and you now have it in a way that does the job of the tire, but doesn't give you the respiratory hazard that you would have, you know, if you work with something that is dispersing. So, for example, we've done experiments where we break the liquid with this material, and we look at particles. The particles are large. We've done experiments with material when it's made into a fiber or a fabric, and what we see is that in the experiments we made, the material behaves like silk thread or silk fabric. But you can't guarantee it's safe. All you can say is that I've done these experiments and I don't have an immune response, I don't have an allergic response, or less irritation, etc. So what one would have to do is we have to continue to do this phase. And also you have to continue to look at the processes, because sometimes even though the material may be safe, something in the process will give you problems. That was the case with PVC, for example. It was the case with pebble. When you found the scale of pebble, they found out at the time of that scale is the polymerization solvent was a suspect of carcinogen animals. And so they went back to the change of polymerization solvent as they were scaling up, because they did not want to have a polymerization solvent, even though there were always traces on the solvent. So you can and you have to do these things as much as possible. The other thing that we're looking at is what happens at the end of life. Like, how is this going to be disposed? The other thing that it looks like this is going to be much more recyclable than plastics. The other thing is like, is this going to be made into small bits? Would you like that?
Well, you're putting it in the soil in pretty small bits, I would think.
In the soil, in that case, for example, it's a political fuse. And what Carrie is looking at is how close is this to biochar? And because when you put biochar in the soil, you look as a way to improve the soil. And it's just the biochar is too expensive right now to buy agriculture. So if one grade of this carbon can be made that is essentially equivalent to biochar, then you won't want to put it in the soil, and then it will be able to biochar. But a lot of these things have to be checked over and over and monitored. Also, because some things eventually you won't see them in the lab. You have to keep monitoring as they go out.
I noticed that you've developed this in academia, but you've got a lot of support from oil and gas industry. I'm wondering how much interactive support you're actually getting from these companies, or are they just throwing money at it, hoping to gain some advertising or anything like that?
a very good question. I can take that one. So when we started putting the carbon hub together, there was a push to do certain things. We said, no, we're going to remain true to the mission. We have a very clear mission. We really want to stick to the fact that we want to make the right forms of solid carbon. So there was some friction with our partners, but because we stuck to our guns, a lot of them have changed their strategy around this area. So I didn't put up that slide, but some of them have started efforts there. They're creating new centers, research centers, to look at using this solid carbon at large scale in the type of applications that we're developing. But you're right, there is a risk, and we don't compromise. We really want to do the right thing. So, and even some of our partners, for instance, in the UK, they look at the money that we want to give them for the projects, and it has to go through a process. They have to review it to understand where is it coming from and what are you trying to do. And they say yes. They say yes, we can get the money because you're staying true to the mission. So it's a very important point you make, and we've turned away people because we had requests that were like, look,
Marie has
not touching
made
it.
an obscure reference that I think we need to clarify. Is, some people here are not in our civil society. Some universities have decided that they will not take money from oil and gas companies unless they will make exceptions if the purpose or the funding is consistent with certain sustainability goals. So what Marie was making reference to is that as we the carbon funding is not only advice, because it was not universities. In some of these universities, we go through this process, and every time the projects were approved, because the project is consistent with positive sustainability mission, not with what is called whitewashing or greenwashing. The other part is that is also that there's a people component. So when you work with a partner, there is an organizational component, it's a people component. And some of the people in these companies who are working with us, they're fantastic scientists. They're actually doing a lot of science to help us. And some are more managing the processes, and that's a little bit depends on who you get. And now we've got 2 cycles, and so we see it's people are people. But I think in general, I agree with Marie, the intent is to collaborate and really participate in the discussion. More questions?
Years ago, plastics was the answer to everything, and today it's coming back, destroying man. It's microplastics, particles. What's to say the same thing won't happen with carbon?
I mean, nothing can say that, right? To some extent, probably there will be, if it is successful, if we go through hundreds of megatons, there will be something that comes out. And in part it's going to be grounded on reality, in part it's going to be hard, right? Because you can go back to the year 1000. Humans have they love to think that they are doing components, right? It's around the year 1000 that they were just thinking that the world is going to end. And then the year 2000, everything was going to crash because of the computer glitch. So I think that maybe this is intensifying. It's because we're more connected, there's more people. But I do think that yes, there will be some unintended consequences of this goes to scale, and they'll have to be corrected. And if you think about the devastation that came with industrializing metals, and also the early devastation of oil mills, it's very interesting to look at pictures of Venice Beach back in the 30s. It was a mess. It was pump jacks after pump jacks everywhere. And now they're still producing gas out of Los Angeles, but they know how to do it by people can go to the beach in Venice Beach and stuff. So I think that I hope we will see that we can be smarter, but I don't think that anybody can be so smart that we catch all the consequences and maybe have to walk away.
So we're going to talk a little bit more about what the carbon hub is doing and how it interacts with organizations.
involved? Or?
We're always looking for more people to come and learn about what we're doing. We have an annual meeting at the beginning of May. It's open to everybody, so you can come hear how we're thinking about it, meet our researchers. We also look for more partners in the corporate space so that we're bringing the supply chain together. So really, even if you think it's very early on, buildings, how would it fit? But we need that pool. We need to have those partners around the table to understand, are we making the right material? Can you use it? Can you apply it? Can you look at what could happen with this material? And finally, we're also looking for researchers, like the little wheel. We do need 100+ researchers because we realize that you really need the best brains around the table. And so by creating this structure, we're leveraging the strengths that are happening maybe in Politecnico di Milano or in Spain. And so we have projects across countries. And you leverage the funding you have, you go a lot further. So we really are open for more conversations, and you should not hesitate to reach out to us, please.
Great. Well, thank everyone for coming. I hope you've enjoyed it. I hope you will come back again to the Science Cafe or other events here at Rice. We really would love to have more of the community here on campus. So I believe Marie and Matteo will probably be happy to talk some. So let's all thank them for supporting us.